Hi, in this video I'm going to show you how to do the continuous convolutions. It's going to be pretty similar to the discrete one, but it's going to work with densities. I will start with recalling what the jointly continuous pair of random variables is. So x and y, a pair, are jointly continuous if the following is true. Take any subset C of R. Well, technically it's not any, so let me put a little star here. Any measurable subset. If you know what it is, that's fine. If not, you'll know this later on. We have the following. The probability, and it's a subset of R square actually, so on the plane. We are looking at sets on the plane, so this is C. The probability that my random point xy is in C is given by the integral of a joint density function. So it's given by the double integral over C of some function x of two variables xy dx dy. Okay? And in this case, this density here, this joint density, well, this function here is called the joint density. Joint density, or if I want to be more proper, then joint probability density function. Now this joint density is a non-negative function that integrates to 1 over R2. Okay? And it's also a simple fact that one can easily check that x and y, in case they are jointly continuous, x and y are independent if and only if f of xy factorizes into the product of two functions, and then it's just a matter of grouping the constants right to find that it's a factor of the marginal density functions for every x and y. Okay? So these are the preliminaries which we need for the convolution of continuous random variables. And so now let's find out. So as usual, let x and y be continuous random variables separately continuous random variables. And here's a note I want to make, that you can have a pair having two continuous random variables not being jointly continuous. So jointly continuous is a bit stronger than the marginals x and y are being continuous. That's just a side remark here. So I'm only assuming at this point that x and y are marginally, separately, as one-dimensional distributions, continuous random variables, but I'm also adding that they are independent. And that immediately makes them jointly continuous by the above formula here, by simply multiplying together the marginal densities. That will give the joint density, and they will be jointly continuous in this case. Okay, then what I want to find out is what is the distribution function first of x plus y at some point A. Okay, so let's start observing this. What is the probability that x plus y is less than or equal to A? Now, according to what we kind of defined before, it's going to be a double integration on exactly this set. So this is going to be my set C, and that set C is measurable, so there is no problem with the definitions. So integrate over this set x plus y smaller than or equal to A. That's my set C. The joint density. What is the joint density? The joint density is the product of that for x and that for y. And then d x and dy. Okay, so how can I make this set a little bit more kind of obvious? Well, I could start my integration in y from negative infinity to infinity. So I can integrate in y over the whole real line. And once that's given, then I need to stop x somewhere. Okay? Then I need to say that x is going to be from here less than a minus y. So I'm going to put here a minus y from negative infinity for x, and then I need to integrate fx x, fy y. Okay, so that's my formula for it. But now you notice something, that I can actually pull fy out of the x integration. There is nothing x in fy, so I can pull that out, and I'm left with the integral from minus infinity to a minus y of the density of x marginally. That is going to give me the distribution function for x. So that is going to give me the integral from minus infinity to infinity. So I'm pulling the density for y back here. And before that, I have the integral from negative infinity to a point of the density of x. That exactly is giving me the distribution function for x at this point a minus y. Just by definition, this distribution function is exactly the integral from minus infinity to infinity density of x dx. That is exactly giving me the distribution function fx at a minus y. Okay, so what I got here is a formula called the convolution of distribution functions. It is a formula that tells me how to compute the distribution function of a sum of independent continuous random variables given the density or the distribution function of x and y. Obviously, x and y have a symmetric role here, so I could swap these two. I could say it's f of y at a minus y, f of x at y. That's obviously the same thing. Now, what I'm also interested in is, of course, how to find the density from here. And I'm going to go back and say that I'm going back to one of these formulas. So again, what I had in the previous slide is f of x plus y at any real number a. So a is an arbitrary real number, of course. This was equal to, at some point, I had this formula here. So let me write up this formula here. Integral from minus infinity to infinity, integral from minus infinity to a minus y, and the outer integration was with respect to y. So one thing I want to do here is, just to make it slightly nicer, I am going to, well, am I going to? Yes, I am going to change x into z. It doesn't matter, of course. I can replace the integration variable from x to z. Let's do that. And fy of y, and then dz. So it's exactly the same formula as before. Okay, now you can see both. So it's exactly the same formula as before. Integral from minus infinity to infinity dy fy. Okay, you have that. Integrate from minus infinity to a minus y, f. Integrate from minus infinity to a minus y, f of x. Okay, so it's the same formula. Okay, so now what I want to do is change variables. I don't like this a minus y here. I want to have a there, so I'm going to change variables. I'm going to introduce, the reason I rewrote everything to z is that I want to use x for something slightly different. I want to introduce a new integration variable for the inner integral as y plus z. So I'm not touching the outer integration, but in the inner one, I want to change to y plus z. Now, if z was a minus y before, then y plus a minus y is going to be a. And if z was negative infinity before, then x is going to be negative infinity. So my new integration will go from negative infinity to a. And then if I want to solve this for z, or rearrange this for z, then of course it's going to be x minus y. So I'm integrating f of x at x minus y and f of y at y. Okay? And notice that what I got is that I have a function. One more thing, sorry, I don't yet have a function, which I want, but almost. One more thing I want to do is I want to swap the order of these two integrations, and then I can tell you what I wanted to tell. Okay, can I do that? Well, I can do that because f's are non-negative, so there's some theorems. Tonelli's theorem actually tells me that we can always swap the integration of the order of two integrations if what you integrate is non-negative and densities are non-negative. So I'm going to swap the integration, and it's quite easy to do so because the boundaries are actually independent of the integration variables. So I can actually swap the order of these two integrals and write this fy of y, and I'm swapping the order here as well, of course, so I put dy dx, and now I can show you what I wanted to show you. So I am integrating a function here, this function here. This is a function that has x in it. It doesn't have y in it because y is an inner integration variable, but it's a function that depends on x. I am integrating a function that depends on x from minus infinity to a, and that's how I get my distribution function for x plus y. From here it follows that x plus y is a continuous, an absolutely continuous random variable with density exactly the box, this box here, that depends on x in it. Okay? So from this formula, because the distribution function of x plus y is the integral from minus infinity to a, where a is the point where this distribution function is taken, because this distribution function is written as the integral from minus infinity to a of something that depends on x, dx, therefore x plus y is a continuous random variable, and the density function can be read off from this integration. It's exactly whatever we see in that integral. So it follows that f of x plus y at a, or at x, let's use x here, is exactly that thing in the box. It's exactly the integral from minus infinity to infinity, f of x, x minus y, f of y, y dy. Okay? And this is the convolution of density functions. Convolution of density functions, or probability density functions. I'm just going to write densities. Okay? People also write f of x plus y is f of x convolution denoted by star f of y. Now, in a previous lecture, we have seen the convolution of mass functions. So the probability that x plus y for integer valued random variables is k was given by the sum of px at k minus I times py at I. And this formula here, maybe I can put them next to each other. Let's put them next to each other. So the sum of the mass function of x at k minus I and the mass function of y at I is very similar to the integral of the density of x at x minus y and the density of y at y integrated out. It's essentially the same formula, the mass function in the discrete case plays the role of the density in the continuous case, and the convolution formula for them is very similar. The notation is also very similar, so f of x plus y is f of x star f of y, means for densities that we have this formula for the convolution of densities. Okay, that means that this density here is obtained from fx and fy this way. All right. Now let me, and then a comment before I show you an example. A comment is that everything we had for, every property we had for the discrete convolution formula holds. So this thing is commutative, it's associative, if I convolve something by itself once, that's just doing nothing, so that's the identity operation. If I convolve something 0 times, that's kind of trivial. And if I have multiple random variables more than 2, if I add like n of them independent, then the density of the sum of n random variables is going to be the convolution of all n densities, in any order one prefers. So all of these statements which we had before for discrete random variables holds true. Now what I want to do next is find the convolution of the uniform random variables, and to do that I'm going to just take 2 uniforms, and the interval will be as simple as possible. It's going to be 2 uniforms on 0, 1. So next, let's do the convolution of uniform random variables. So example. Let's take x a uniform on, and for simplicity let's keep it 0, 1, and y uniform on 0, 1, independent. And let's find out the density of the sum of them at some point A. Well, let's use x as before. Let's use x. Okay. In other words, let's find out the convolution of fx with fy at x. In other words, density of the sum. Now, x plus y is 2 real numbers between 0 and 1. So if I add them up, that's going to be between 0 and 2. And let's actually do the calculation. So f of x plus y at x, according to the formula, is the integral from minus infinity to infinity, f of x at x minus y, f of y at y dy. Now what are these densities? So these are the marginal densities for x and y, respectively. And this one here is just 1 when x minus y is between 0 and 1, right? It's 1 when x minus y is between 0 and 1 because x is uniform on the interval 0, 1. This interval has length 1. The density of the uniform is reciprocal of the length. So this is going to be the indicator that x minus y is between 0 and 1, which is also the indicator that, let's solve this for y. So y is going to be smaller than or equal to x, and y is going to be larger than or equal than x minus 1. Okay, so that's the first indicator. The second density, or the second indicator, is that of y between 0 and 1, which is already solved for y. And so I have actually 2 competing boundaries. I have a boundary of 0 for y, and I have a boundary of x minus 1 for y on the left hand side. And I have a boundary of x on and the boundary of 1 on the right hand side. So another way of writing this integral is that if any of these boundaries is violated, if any of these indicators are 0, then of course the whole integral will be 0. So y is not allowed to go above x, it's not allowed to go above 1, it's not allowed to go below 0, it's not allowed to go below x minus 1, because then the integral is 0. Otherwise, the integral, what I am integrating is 1. So I'm going to integrate from both of these lower bounds need to be satisfied. So I'm going to say that it's the larger of them, the larger of 0 and x minus 1. Okay? This is a notation for the maximum or the larger of these two numbers. So whichever of 0 and x minus 1 is the larger, that's where I go from. And I need to satisfy both these bounds for y on the right hand side as well. So it needs to be smaller than or equal to x, it needs to be smaller than or equal to 1. So I'm going to put the smaller of x and 1. And this is the notation for the smaller of the two. So if x is smaller than it's x, if 1 is smaller than it's 1. Whenever this is satisfied, then I'm integrating the product of two 1s for the indicator, which is 1. So that's what my integral is. Now, if x is smaller than 0, so let's evaluate this integral. If x is smaller than 0, then the upper bound is lower than the lower bound, and it's understood that the integral is 0, and indeed then the indicators cannot be both satisfied. If x is smaller than 0, then y is smaller than that negative number, but it also has to be larger than 0. So then the answer is a big 0. Similarly, if x is too large, if x is larger than 2, then let's see what happens then. Then 2 minus 1 is 1. If x is larger than that, then this is a number larger than 1. And I have to start from here because that's larger than 0. So I have to start from x minus 1, which is larger than 1. But I cannot exceed 1 up here. So again, the integration is over an empty interval. So again, the answer is 0. Okay. Now, clearly at x equals to 1, there is a change in the boundary here and also in the boundary there. So the next interesting case, if x is at least 0, but at most 1. If x is at least 0, but at most 1, then I'm integrating from, if x is positive, but at most 1, if x is smaller than 1, then x minus 1 is less than 0. So I am integrating from 0 in this case. And if x is smaller than 1, then I can only go up to x, because I have to take the smaller of the two. And of course, this gives me x. Okay? And finally, if x is between 1 and 2, then I need to integrate on the lower boundary. If x is larger than 1, then x minus 1 is going to be larger than 0. So it's going to go from x minus 1. And on the upper boundary, if x is larger than 1, then the smaller of the two is 1. So I'm having 1 here. That gives me 1 minus x minus 1, or 2 minus x. So that's the case when x is between 1 and 2. Okay? All right. So these two are expected, right? That when x is negative or when x is larger than 2, I have a 0. That's expected because the sum should be between 0 and 2. And indeed, between 0 and 2, I have something non-trivial. Notice that x equals to 1 is valid in both cases. X equals to 1 gives me 1 here. It also gives me 1 there. So that's a continuous function. And I can take a look. I can look at either of these two cases at x equals to 1. And so let's plot this function. So the joint density f of x plus y at x is going to go 0 up to 0, and then 0 above 2. It's going to be the identity function between 0 and 1. And it's going to be 2 minus x, which has a 45-degree negative slope. And at x equals to 1, it's height 1, so it's going to continue here without a jump. And it's going to look like this. So this is at height 1 here. Okay, that's the joint density. It's easy to see that it's actually density. It's the area under this curve is a triangle of base 2 and height 1, which is of area 1, so this is a density. It is not uniform. X plus y is not uniform because this density is not a constant. Okay, uniform has a constant density on the interval. This is not constant. It's more likely to see x around 1 than close to 0 or close to 2. Okay, so this is not uniform. Also, if anybody remembers the mass function of rolling two dice, so two dice are rolled, add the numbers up, look at the mass function, that will actually have the discrete analog of this density. It will have a discrete mass function that goes linearly up until the sum being 7 and then goes down linearly until the sum being 12. It's the discrete analog, the discrete uniform analog of this one.